process plant. And no problem. Alright folks, let's get to work. I'm Mike. I'm a senior engineer and also the process director of our process plant.
Hello, my name is Aiman Syahmi and I am the reactive system specialist.
Hello, I'm Nurulain. I'm the fluid flow specialist.
Hi, my name is Nurjeha Qistina.
I'm Anis, the narrative system specialist.
First of all, to design a process flow diagram, we will apply the knowledge from two courses, which are Principle of Chemical Engineering and Chemical Engineering Fluid Mechanics. Principle of Chemical Engineering provide us the ability to compute mass and energy balance in processes. Of course, it includes a complex compilation of equations which will be discussed later. This helps us to understand the amount of compound and energy involved in the process. Next, by applying the principles from Chemical Engineering Fluid Mechanics, a piping system which aids the production and minimize energy loss at the same time maximize efficiency can be implemented. Now, let's look at the PFD we have developed for isopropyl alcohol production. You can pause if you want to look into details. In short, propylene and water are fed into a reactor as reactants to produce IPA, isopropyl alcohol, under Tokuyama process. Then, the mixture of IPA and excess water are purified by passing through a nitrotropic column and two distillation columns. The final product is IPA solution with approximately 70% purity, which will be used for commercial purposes.
Moving on to the non-reactive system, for the mass balance, the inlet is assumed to have a flow rate of 200 mol per hour of 63 mol% of isopropyl alcohol and balanced water. The top stream of the outlet contains 70.56 mol% of IPA. From the flow diagram, there are three unknowns and three independent equations identified, which resulted in 0 degree of freedom. The value of unknown, the mass flow rate, and the mass fraction is calculated. For energy balance, the mixture of isopropyl alcohol and water flowing into the distillation column is in vapor state at a temperature and pressure of 110 degrees Celsius and 5 atm respectively. Both products coming out of the top and bottom stream are in liquid state at a temperature of 60 degrees Celsius, while the pressure remains unchanged. The reference point for both compounds is 60 degrees Celsius, 5 atm, and in liquid state. The value of specific heat and heat of vaporization of IPA are obtained from reliable sources in the internet. For the first specific enthalpy, there are change in temperature and state, which resulted in 46.56 kJ per mole. The same goes for the specific enthalpy of water in the inlet, which resulted in 44.01 kJ per mole. Meanwhile, the specific enthalpy of water and IPA for the outlet are 0 as they are in the same state with the reference state. The change in enthalpy is calculated by using the formula of summation of outlet molar flow rates times specific enthalpy minus the summation of inlet molar flow rates times specific enthalpy, which resulted in the value of negative 9123.3 kJ per hour. As the change in enthalpy is equal to the heat release is found to be negative 9123.3 kJ per hour.
I will be talking about the reactive system in this chemical process, which is the first reaction. Two pipes which contain both propane and water are flown into the reactor. In this reaction, propane undergoes addition reaction with water to form a new compound, which is called isopropanol. The reaction typically occurs in the presence of an acid catalyst, such as sulfuric acid or phosphoric acid. After the reaction is finished, some of the isopropanol would react with itself to produce diisopropyl ether and water. To calculate the isopropanol produced, we must first do the mass balance. First, we will calculate how much propane and water are flown into the reactor, and from there, using the chemical reaction, we can calculate the amount of isopropanol produced. After we are done with the mass balance, we will need to do the energy balance. We will ignore the pressure change during the calculation since isopropanol is an ideal gas. Before we start doing the energy balance, we will need a reference state, so we will be using 25 Celsius as our reference state. We will calculate the enthalpy produced for both input and output using the reference state and using the respective formula. After we have calculated the enthalpy produced, we can multiply it with the respective mass that we have calculated during mass balance and get the total energy produced.
These are our piping layouts. We used the 4-inch schedule 40 stainless steel pipe with outlet diameter of 4.5 inch and inlet diameter of 4.026 inch, and for fittings we used 8 standard 90 degrees elbows, as well as 1 wide open globe valve. Next is our table of summary of pipeline pressure drops across all pipeline. For pressure drop at reactor to azeotropic column, we got the value 96400.3384 Pascal, and for pressure drop at distillation column to buffer tank is 0.0994 Pascals. And lastly, these are the flow of calculations to find the pressure drop. To find the pressure drop, we first calculate the velocity, then the Reynolds number, and then the friction factor, and lastly the friction loss. Then substitute the values into the Bernoulli equation, and we'll get the pressure drop.
Now, let's talk about the pump power. In order to calculate the pump power, few assumptions can be made. The flow of fluid is steady. All fluids in the calculations are incompressible. To calculate pump power, the pipe pressure drop across the pipeline is assumed to be negligible. Tank is very large, thus velocity of isopropyl is equal to V1 equals to 0. The pump increased the initial velocity of fluid flow to V2 equals to 3 meter per second. Efficiency of pump is 90%. Before we proceed, here is the flow of our calculations. We will be using continuity equation to find our mass flow rate. Next, characterize the Reynolds number, whether it is a turbulent flow or laminar flow. By referring to the table, we will be able to calculate the friction factor of pipe flow as well as friction loss. Based on Bernoulli equation, work pump calculation can be solved, which leads to our final calculation of pump power. Value gained is 4.21 kilowatt. Let's proceed to our strategy to deliver isopropyl alcohol to storage tank. Firstly, by safe and efficient handling. Isopropyl alcohol is stored and transported in liquid form for ease of handling and utilizes a pump for efficient transfer. Stainless steel tanks and pipes with excellent corrosion resistance ensure product purity and minimize contamination risk. Proper welding techniques, as recommended by industry standards, guarantee the integrity of these storage systems. Next, through maintaining product quality and safety. Stable liquid levels and inert gas padding will prevent moisture absorption and oxidation that preserves the quality of the alcohol. Low flash point necessitates measures like inert gas padding and proper selection of complementary materials, namely flame arresters and explosion-proof equipment to minimize fire risk. Last but not least, by prioritizing environmental considerations. Insulation on pipes helps maintain optimal temperature during transportation, which reduces heat loss. And grounding the storage tank will prevent static discharge hazards. Here's the main plan of our storage tank specifications. By a thorough calculations, it can be noted that IPA produced per day is 4,324.52 meter cube. Some justifications were met while choosing the value of our specified storage tank and its capacity. Firstly, tank height is chosen to be 22 meter, while tank internal diameter is 25 meter. It is justified that a maximum operating volume is able to proceed while also includes an additional space for liquid expansion. Next, tank wall thickness is 10 meter as it is able to restrain high pressure. 300 series stainless steel is suggested to be the material of tank and pipe as it is able to withstand corrosions. The inlet line is 4-inch Schedule 4 stainless steel, which emphasizes its high durability. The value of inert gas padding will be 0.5 meter and pressure of tank is 15 kPa. Temperature of tank will be 5 degrees Celsius to keep the tank in low temperatures in order to reduce hazard.
In order to develop a safe and efficient isopropyl alcohol production plant, we rely heavily on the knowledge and skills gained from chemical engineering fluid mechanics and principle of chemical engineering courses. The principle of chemical engineering enables us to calculate precise enthalpy changes and component ratios, minimizing waste and maximizing production. By controlling heat absorption and release, we ensure the reaction temperature remains within safety limits. Chemical engineering fluid mechanics aids in optimizing pipe design, allowing for swift fluid flow to storage areas. Through careful selection of materials and dimensions, we minimize friction and manage pressure effectively. This enhances plant design while reducing energy consumption.